Catarina. I work at LOBA, and we are the dissemination and communication leaders of Evolve, and we will be moderating this fourth webinar of the Evolve webinar series. So today our webinar is about using Evolve technologies for different tools based on Earth observation data. We will have speakers from our partners organizations, which are THALS and Alinea Space, Space Hellas, and Cibel Tech. The objective of this webinar is to show the interest of digital technologies such as parallelization frameworks, stream analytic engines, fast storage, or hardware accelerators that can bring to different sectors based on Earth observation data. This webinar will be divided in 3 parts. First, we will talk about maritime surveillance, and second part, change detection, and third part, our agriculture use case. So I think now we will start with Dr. George Kardikis from Space Hellas. So I give the floor to you.
Thank you very much, Katarina. Good morning, everyone. Thank you for attending this webinar. My name is George Kardikis. On behalf of Space Hellas, I will present you the implementation of one of the use cases of Evolve, which is around maritime surveillance. Okay, so starting with a few words about our application. So maritime surveillance is a very, very wide application area, and one can make use of different diverse information data sources. In our case, we are focusing on 2 different sources of data for augmenting the maritime situational picture. The first one is satellite imaging, and more specifically radar images, SAR, synthetic aperture radar images, on which vessels are quite easy to spot on the open sea. The second source of information is AIS data. For those of you who are not familiar with the technology, AIS is a kind of signal which is broadcast by large vessels, reporting their status, their position, their name, ID, and so on. And these signals are collected by a network of terrestrial receivers and are fused together in a GIS system. So we are using these 2 types of data, as you see also indicatively in this screenshot, and we are trying to combine them and augment them in order to present the user with a picture of the maritime, of the surveillance of a specific region. So prior to Evolve, this application was already developed and was already in operation. However, in the project, we had to do several evolutions and transformations in order to allow our application, our maritime surveillance application, to take advantage of the advances of the technological advances which were offered by Evolve. So one very basic transformation was that we had to migrate from the old monolithic application to a scalable cloud-native workflow in which every stage is organized as a container. And at the same time, to further increase the performance, we had to exploit state-of-the-art frameworks for big data and machine learning for scalability and parallelization. I will go into more details in a slide just afterwards. So the goal for this from this evolution will be, first of all, to decrease the processing and the response time, and also to increase the spatial and also temporal window which the application processes. This is not only about increasing the coverage of the scope, let's say, of the application, but also increasing the accuracy of the machine learning mechanisms, because the more data they have, the more accurate predictions they can make about the course or the behavior of a ship, as we will see later. So I'm going to go over briefly the different stages of our workflow in order for you to better understand how the application works. So the first stage, as you might imagine, is the acquisition of data. So the acquisition of AIS data, the signals which the ships emit, are done by both a private network of receivers, and also an external AIS data provider with which we have collaboration. The second type of data, the satellite images, they can be downloaded either from a satellite hub or from a patrolling aircraft. You can also have radar images from aircraft in order to have a higher resolution. In our case, we are using scenes from the Sentinel-1 satellite, which are openly available via the Copernicus hub. The third step is the detection of vessels in the satellite image. In our case, we are using a library which has been open sourced by ESA and the European Commission, the SUMO library, which is specifically developed for vessel detection on SAR images. The same library also implements this next step, which is the classification of the vessel type using the feature extraction. It's mostly at this stage, it's mostly about the size of the vessel. Now, having these two types of data, AIS and SAR, we can combine them and try to match the targets on the SAR image, the vessels on the SAR image, with the information we have from AIS. And by this correlation, we can easily detect the vessels which are visible on the satellite image, but they do not emit an AIS signal. This is something which is not normal, because the vessels which are quite large to be visible on the SAR image should be obliged to emit AIS information. That's why we label them as non-cooperating vessels. There are vessels who need to be further investigated. Another task which also runs is the anomaly detection part on the AIS stream. So we use a series of AI algorithms to identify possible anomalies in the AIS data streams. Some obvious one can be, for example, intermittent signals, changing the vessel identity and route speed changes, and anything else which deviates from a normal AIS stream, which is normally emitted by a vessel. So all these vessels which on whose track we identify as anomalous, we label them also as possible vessels which need to be further investigated. And of course, the final step, because we need to somehow present this information to the end user is to visualize the products of our processing. We present them in as an integrated maritime situational picture in native GIS-based GUI. This is an illustration, a visualization you will see later in the live demo of the different stages of our workflow. You see the first stages, which are about acquisition, then the SAR image processes, which we take advantage of parallelization in order to be able to process different scenes at the same time. And by this approach, we managed to decrease the processing time significantly. And then it's the anomaly detection and the final visualization part. Now, I don't know if you have been if you are already aware of the features which have been provided by Evolve to the different use cases, to the different applications in order to increase their performance. Evolve actually brings together 3 different domains, HPC, cloud, and big data. So in our application, we took advantage of features and enabling technologies from all 3 domains. So we take advantage from storage heterogeneity and coarse-grained parallelisms, as I already showed to you, for accelerating processing. Our workflow was based and was deployed using state-of-the-art cloud technologies such as Argo for constructing and defining the workflow, Kubernetes for orchestrating the containers, and a notebook front end. All these are offered by Evolve, and notebook front end for interacting with the data. And in the back end, we also took advantage of big data enabling technologies such as Kafka for real-time stream ingest, Spark for distributing processing, and the multi-stage workflow, which is the structure which our application follows. That's it from my side. I will now hand over to my colleague, George Vambakas, who will present you a live demo of the application and how it has been deployed in the Evolve cluster. So you will see all these steps in action. So George, it's your turn. Please make sure to unmute.
Yes, just a moment, please. Okay. Can you see my screen now?
Sure.
Hi, this is George. I will present you a demo of the workflow regarding maritime surveillance. All images and Docker images have been deployed. Can you hear me?
Yes, George. Yes.
Okay.
Loud and clear.
All right. Thanks. All Docker images have been pushed to the private registry of Evolve platform. And our workflow has been deployed using Apache Zeppelin. This is the platform that we used that's based on Apache on Zeppelin. So this is our services running here. You can see our services. Just a second. All these services that we have deployed. We have also, deployed 2 cron jobs that collect data from Copernicus Open Access Hub and stores them to the platform for further processing. And we have also deployed a continuous running pod that collects AIS data from AIS transmitters and stores them again in a database. You can see it here, for example, here is the latest SAR images that have been downloaded. And here you can see the latest AIS data that we have. All images are being stored as an actual file, zip files in the platform. So you can see here that we have actually a lot of that images. And so having these images and the AIS data, then I can continue to our workflow. This is actually our workflow regarding maritime surveillance. It's a mix of paragraphs, of Zeppelin paragraphs, using Postgres, Python, Angular, and scripts in order to trigger the Argo workflow. The user only needs to enter a time period he wishes to check, and then just clicks this button here that says run all paragraphs, and the workflow will be executed. Sorry. The first step is actually collecting data, appropriate data, based on the criteria of that the user entered. And this also instantiates a workflow. You see here that starts a workflow, an Argo workflow based on the images, the SAR images that were found during here. You can see that 3 images were found based at that time, in that time period, sorry. You can also see that also here. Just a sec. You can see the steps of the SAR image process, not the SAR image process, sorry, the workflow itself. Here you can also see here the log files while vessels are being detected. Both the image processing algorithm results into an XML file, something like this. No, you cannot see that, can you? Anyway, in an XML file that has the positions of the possible vessels detected. Now we can see that the SAR image process has already finished for these 3 images, and then the anomaly detection algorithm procedure takes place. Here, first, there is a pre-processing step in order to extract features and normalize data, and then the results are fed to a predefined model, a pre-trained model, sorry, in order to detect anomalies. So you can see that it's already finished, and now so we can see the results here. Sorry. So these are the results. The red dots indicate the possible vessels detected by the image processing algorithm, while the green ones are the correlation between the AIS data and the vessels detected by the image processing algorithm. This means that the vessel that has been detected is true, since there was also an AIS signal from that time period in that area, and the purple ones are possible vessel detection anomalies based on vessel trajectories or something like not normal AIS transmissions. So you can see there that we have a lot of vessel detections based on the images and a few correlations with AIS data. However, this is so because we have actually a transmitter here in Athens and a smaller one here in Lesbos Island. So we don't have actually data from here, OpenSea. So that's it. I don't know if you have any questions.
Thank you, George. Any questions you can type in the Q&A box.
Okay.
You are, Katarina, you are mute.
Thank you, Michelle. So if there are no questions for now, we can move on to the second part, but you can still make questions for this part and we may answer in the end. So let's move to Miss Michelle Obran that will talk about the change detection workflow. Thank you.
Okay. Hi everybody, so I'm Michelle Aubrin. I'm a data processing engineer in Earth observation at Thales and Aerospace, and today I will talk to you about our change detection tool. So I will share my screen. Okay, so the goal of this tool is to detect the generic change ARA on Earth observation satellite images. So here we have two images from the same ARA, but that has been taken in a different date. So the first step consists in project these images in a more robust space. To do this, we use a neural network model. The goal of this new feature space is to be robust to the noise or also to be invariant to the lighting or atmospheric conditions that are not a relevant change in your case. Once we obtain these two new representations, we can make the difference between them to get our change detection map, as you can see here. So in her case, the yellow ARA represents windward that has been affected by frost. So this is our pipeline. So the pipeline is composed of 4 modules. The first one, named PEPS download, consists in searching image in the PEPS platform that match a query on the ARA and the date of interest. Then when he finds the image, in download them with their metadata. The second module consists in extracting the bond of interest in each product to concat them, maybe also resize them if the bonds are not in the same spatial resolution, and to convert them into GeoTIFF images. The next module, named extract info, consists in extracting the metadata from the images, from the GeoTIFF images, mainly the date and the ARA. Then it will group all the images by with the image that represent exactly the same ARA, and it will sort them in a chronological order in order to create time series. This module is really important because it will determine on which couple of image we will compute our change detection map. That is the last module that I just presented to you just before. So what I just presented to you was what we have before to integrate the Evolve project. So as you can see, the pipeline was run in a really sequential manner. And the objective to integrate the Evolve project was to benefit from the Evolve technology proposition to automate the pipeline and to increase the processing time. So now I will present you a short demonstration of the pipeline in Evolve, the new pipeline.
Hello everyone, and welcome to the chain detection pipeline demo in Evolve. So we actually start from the Evolve dashboard, where we need two services, an Argo service and a Zeppelin service. And inside the Zeppelin, I've created a notebook where we only need the function run chain detection pipeline, which I've already uploaded into the Evolve dashboard in the file section into a folder called chain detection. So this is a Python function, and so the first thing I do is to change the directory to actually be able to make the import. So the chain detection pipeline is the function is really simple. We just need a name for the job and a right directory. So I've chosen the local chain detection demo. So we need to create this directory in the files section. Cd demo. And we can see the folder is empty at start. Then the function needs like the email and password credentials for the PEPS account, a location, and a time period. In this case, I've chosen from the 25th of April to the 1st of May. We can also choose a cloud criterion, but for this case, I've just left the by default 100. And so if we execute the function, it will automatically create a Argo workflow with the name we've chosen, and we can actually see the logs of this workflow. So we can see the first thing it does is to actually contact the image provider and download the metadata of the request. And he's gonna then notify us about all the status of the different images that are actually going to be processed. We can see it has started downloading the first image, and we can see it in the right folder we've created inside the Sentinel-2 products folder, which is actually the download folder. And here it is, the temporal file where it is downloading the data. What is happening in the backend is that the run cd pipeline function has created a PEPS download module with information of our request, and it has contacted the PEPS platform to get the metadata of this job. The metadata is something like this. It contains all the images that match the query with the ID and coordinates of their position. So PEPS download will send this information to extract.info, which will actually process the different images and will make some couples of images that we call sets, and we'll select the images with interesting information. So we'll send these images back to PEPS download, and PEPS download will start downloading the first image. So after waiting a while, we can see how the first image has finished downloading. And if we update the logs of the container, he will tell us indeed that the first image is downloaded and he has already started to download the second image. The first thing that Peps Download does when it has finished the download of our product is to notify GPT-TIFF, and it will start downloading the next product. GPT-TIFF it's a module that will get the downloaded product, and it will extract a TIFF image and a mask, a cloud mask associated to this image. So once it's done, it will then notify extract info to let him know that the image is ready to be processed by the chain detection module. So if we update the logs of the container, we can see how there is a new notification that is telling us that the first image is now ready. This means that the GPT-TIFF module has finished processing the product. And if we go to the TIFF images folder, we can see how indeed the mask and the TIFF image are now there. If we wait a little bit, there will be more images with the ready flag and the stacked info, which is always observing the different sets. When it detects a set with all the images ready, he will send a message to Argo events who will be in charge of contacting Kubernetes to generate a pod with a chain detection container. This chain detection container will process the two images to generate the chain detection maps. If we keep waiting, there will be more sets with all the images ready, and so Extract Info will send more messages to Argo event that will generate more chain detection pods. So this will keep going until all these sets of the job are finished. If we update the logs one more time, we can see that the second image is also downloaded. Here it is. And now GPT-TIFF is processing the product to generate the mask and the TIFF image. This process normally takes like between 30 seconds or 1 minute. We can try updating the logs, and there we go. Now the second image, we have received the notification of the second image being ready. So Structure Info has dispatched this set. This means that the message has been sent to Argo events by Structure Info, and when the chain detection pod is generated, he will notify us by the processing tag. So now the chain detection pod is processing the two images to generate the chain detection maps. This process normally lasts for a little bit more than a minute. In the meanwhile, we can see how the two images and the two masks are now in the TIFF images folder. And for now, we can only wait for the chain detection pod to finish. So I think I will skip a little bit the video. So after waiting a while, we can now update the logs, and we can see how indeed the set is now finished. As it was the only set in this job, we can see the message that the job is also finished, so the container is exiting. And if we go to the results folder in our right directory, we can also observe how the chain detection pod has written the result file, the chain detection map, into this folder. So with all this, we can now download the results in an easy way, and the pipeline is finished. Thank you.
So this, what we present to you was the pipeline at the month 18 of the project. Since then, the pipeline has already been modified. You can see the new pipeline here, and the big changes is that the JPEG tutif pod is not permanent anymore and is called by Argo event, like change detection module. Here I will do a little summary of the technology used. So first we have used use the Docker container, but this technology was already used before to integrate Evolve project, and it was the only one that we used. And since we integrate the Evolve project, we have used a desk scheduler to have parallel computing inside the change detection module, that is our main module, and that is the module that takes the more time. We have also integrated Kafka in order to make our module communicate between each other. And by doing that, we can have a coarse-grained parallelism. And the advantage also of Kafka is that you can, if you look the log, you can be aware of the current status of your pipeline. We have also integrated FOST that has been integrated only in the extract info module, which is the pilot module of our pipeline. And what FOST do is that is register the change log in a Kafka topic. Like that, if our extract info module fail, the pod fail, it will be deployed again, and the FOSS will get back the change log, and like this, the pipeline will not start over from the beginning, but it will know when he has to, what has already been done, and how was the pipeline when where the module failed. We have also used Argo event to create a Kubernetes pod from Kafka messages, and by using this, we can release the resource once the process is completed, mainly when the change detect the JPEG tutif or the change detection module are finished. And finally, all the pipeline is running from the Zeppelin notebook. Here I will talk about our performance in terms of computing time. Actually, we are currently at this step to monitoring this performance. So before to integrate the Evolve project, the pipeline takes about 30 minutes to run. So the pipeline was really slow, but as I explained before, we run it in a sequential manner. Since we have integrated desk, the computing time has been divided by 10. And when we have integrated Kafka, we again decrease the computing time. So now it takes a little more than 6 minutes to run 5 change detection maps. So thank you for your attention, and I'm here if you have any question.
Okay, our audience is quite quiet today, so we will move on to the third and final part of our webinar. This will be about our agriculture use case that will be presented by Sibeltech and by Mr. Teddy Debrutel, if I'm saying correctly. So please go ahead.
Yes, hello everyone. I'm Teddy from Sibeltech. So my presentation. Oh, it's good. So I will present you the company, the two products that we develop in the Evolve project, and how we participate of the Evolve project. Sibeltech is a young company created in 2011 to meet the need to help the agricultural world understand the evolution of crops. This company is based in Paris and Orléans in France. A large part of the employees are engineers. We have a sales representative in France and one in Italy. The main line of research are modeling of plant growth, the installation of the sensor in the open field or in greenhouses, statistical processing and data assimilation methods, signal and imaging processing, IT architectures and service platform, and data analysis and visualization tools. We are developing two products in the Evolve project: the automatic recognition of cultures from satellite images. This crop monitoring allows the automated estimation of the areas of an definite geographical area. The result is sent to a platform accessible from a computer, tablet, or a smartphone. In this image, you can see the detection of the following crops: corn, durum wheat, soft wheat, barley, rapeseed, and beet. The second development is crop growth simulation. From various input parameters such as soil data, weather, sown crop, we will simulate the growth of the plant in order to estimate the yield of a plot. This work also allows adapt species to paleoclimatic parameters, optimizing the use of input by better matching the real potential of plants, adapt the sowing densities to the soil potential, adapt irrigation needs, adapt the use of fertilizers to the real potential of the crop, limit CO2 in greenhouses, promote the use of biocontrol, pesticide solution, improve the sanitary quality of production, zero phytosanitary residue, zero contaminant, improve the nutritional and taste quality of production. So, Sibeltech is positioned on the global cycle of the plant, from the varietal selection phase through the production phase, while working on the first transformation phase. Thanks to the multidisciplinarity of the team, we can work in various fields: agronomy, information processing, web interface creation, data security, artificial intelligence, image processing, in order to best meet expectation for our clients. Thanks to the large computational capacities of the Evolve supercomputer, we can speed up our processing and increase the geographic size for crop detection. This process consumes energy in RAM memory and data transfer. This project also allows us to improve the transition for our algorithm from the development stage to the production stage. We have developed the different algorithmic steps in Docker container. With this technology, it is easy to go from development on our computer to execution on a HPC. Docker also simplifies parallelism across multiple nodes in a cluster. Our process orchestration is done with Docker Compose. You can use a graphical interface to quickly develop codes in several programming languages. In this project, we are users of the different technologies developed. We help design requirements. We test the Evolve interface on the workflow with challenging codes. We participate to automation development. We benchmark technologies together, and we improve the code workflow. Here is the general flow of our acquisition chain, from imagery to the yield of the plot. We have set up a database listing the satellite imagery data necessary for our algorithm. Docker container with TensorFlow work with GPU for the crop recognition part, and the container with MPI for the simulation of the growth of the model of plant. On the region where we want to know the cultures present, we will load the corresponding images in order to determine the culture. We have one CNN model per culture. Then we will create false color images with the detected culture. This image will be used as input for the plant growth simulation. We use IME technology to speed up the transfer of images. Satellite images come from open source providers like Copernicus and SciHub. For the second step, the state of the soil plant atmosphere system is simulated day after day, taking account soil composition and climatic data of the day. At truth, this is an exciting approach that opens up new possibilities. Plant growth model have margin error because it's not all mechanistic processes on described in the model. For instance, the model will not simulate pest disasters. The mechanist processes included in the model are never completely accurately described because we are trying to model a living system, that the plant. To correct for this error, we use a data assimilation method, much like Kalman filtering for linear system, thanks to data for plant development coming from remote field sensors occurring during the growing season. Model simulations are corrected online during the season using such data. For simulation, we can estimate the yield of crop over region. So, in this project, we spent 2 years implementing the different technologies and consolidating our pipeline. Since January, we are testing ways to optimize the code execution to reach those results thanks to Evolve. Our current work is to decrease the error of the plant growth model by increasing the number of simulations. Thanks for your attention. Do not hesitate to contact us if you have more detail on specific points.
Okay, thank you. It seems we have no questions again. So I think we can give this webinar as finalized. Thank you everyone who attended. We will have our final webinar of this June set happening next week. It will be about leveraging heterogeneous acceleration technologies for cloud HPDA platforms. It will be presented by the Evolve platforms from Atos and from ICCS. So please join us. It will be the final webinar. The next round of webinars will happen in October with 4 more webinars. Don't forget to register to the Evolve newsletter to receive the latest news about our webinars and other updates of the project. So if there are no comments, thank you. Thank you to our speakers also, and see you soon. Goodbye.
Thank you. Bye.
Bye.